Welcome to Calculus in the AM. Your host, Mr. Sandalka. Let me pause while I update my attendance and then... You'll never guess who I saw the other day. A while ago, I was in Washington. Who is that? You'll never guess. I said you'll never guess. Well, is it him or is it her? Oh, I'm on a mission. Let's make calculus great again, kids. I love the poorly educated. No, you guys aren't gonna be. You guys are gonna be sick of getting things right. I was like, oh, Mr. Sandalka, please stop getting questions right. Please stop teaching us so good. Okay, let's finish this sucker. Now, curve sketching. I have the last question. I said you could start on it because you know how to do most of it. And you actually know how to curve sketch. But let's fit this in with calculus skills and stuff like this. So the very first thing is, I'd say like your ABC on the last question, like that one that goes 7 A, B, C, D, up to I or something like that with curve sketch. The first thing, whether you do it in this order or not, is take the derivative, first derivative, set it equal to 0, find the critical numbers, find the increasing and decreasing intervals, and maxes and mins. Now I consider that 4 things, but they're all a connected process, whichever order. So when you're doing your process, when you're doing your problem, think of A, B, C, D, think of it all at the same time. Let's do this here. So let's rock this. So I'm gonna do the following all at the same time here. So first derivative, and from what does the first derivative tell you? It tells you possible maxes and mins, right? Critical numbers, extremes. So critical numbers, which are extrema, are possible, and then increasing, decreasing intervals. But I'm just putting this down. We're all going to do this whole bit on here. We're going to use sign analysis to tell us. So let's go with our first derivative. Now, I give you a function with a cube on it on purpose. If this was not a cube, I would suggest multiplying out and doing your calculus that way, right? So this one is too big, too much, it's way more work to multiply it out and you'll probably make a mistake. So you're going to do this derivative. I'll give you guys a second here to do the derivative. It's the 2 combination rules, right? Chain rule and product rule. I'll give you a minute, I'll pause the video. Make sure you do it, videos. Let's go through it then. I did the derivative of the first thing. Yeah, 3. I even did the derivative of the inside, but it's 1, right? Leave the second thing alone. Wow, my coffee's just steaming. First thing left alone, like you said, what happens to the x plus 2? The derivative of that is just 1, right? So nothing to do. However, we've done the calculus. The rest is the algebra. Because can I tell what you're looking for critical numbers? This is a polynomial, so you'll never have... You should actually ask yourself this before you even start the problem. Is there any domain restrictions? No. There'll never be any values on this derivative either where you can't do the derivative, right? Undefined values. So it's strictly zeros we're looking for. And it's not... I can't find zeros easy unless I can factor it, right? So you need to factor this. We say what's in common here? X minus 2, and you take the lowest degree always of the square. So I'm taking out x minus 2 squared. I'm going to use a big old bracket. And I won't show more than one step at a time. And once you do that, I think you guys can tidy some things up. I'll give you a second to do that. Okay, so moving along, hopefully you got this, and then you take out the common factor, 4. Because I'm looking for a critical number though, what do we need to set this equation, this derivative, equal to? 0. So we're looking for the horizontal tangents. 0 is equal to 4. I'm pulling that out from the second bracket. X minus 2 squared, x plus 1. Now, I think it's fairly simple to see where the zeros are. If x minus 2 equals 0, that'd be because it is positive 2. So there's a critical number possible here. It's a critical number. It's a possible extreme. -1. We'll see if it's an extreme. Right away with both of these. What's the best way to examine this so we can figure out what the extrema and increasing, decreasing intervals are that we're using? Sign analysis, right? Little number line. So we're going to do some sign analysis. So I'm only putting on these two values, -1, 2. We know that zero's in between. You don't need to plot everything else. You list your derivative on the side, including the +4, because if that was -2, it would actually change signs and stuff like this on things. So that's why I put it there. Or if that was 4x, I would still put that as 4x. So I'm going to put the +4. It never changes signs. X minus 2 squared, that's important, x plus 1. Now, do we all know how to do a sign analysis? I'm sure hoping. In each zone, +4 is always positive. 4 doesn't change. Then I take a look at x minus 2 squared. Okay, we obviously get a 0 here, but because it's squared, anything higher is still positive, anything lower is still positive. That's important. And then the last one, x plus 1. If I had -1, I get a 0. If I test with -2 or anything smaller than -1, I'm going to get a negative value. Positive values for anything higher. Now, in our summary, if we plug in values smaller than -1, we're going to get negative out of that. So, zone of negativity. This is my classroom most times. People come here to feel bad and be insulted. Then, positive, positive. It doesn't change signs. So, you know how I said 2 is a critical number? But because it doesn't change signs, is it a max or a min? No. Now, this isn't required, but it's going to help you. Underneath here, draw a stick diagram. Don't worry about curviness. Right? This negative means it's falling. The original function is falling. This means it's increasing. It might level out at 2, but it never decreases. And then it keeps increasing after that. Because it has a slope of 0, right? That's why I put a flat line underneath the 2. So concavity, I'm not worried about. But now we can answer our questions. Or questions. Maxes and mins and where it's increasing and decreasing. Like I said, those A, B, C, D, the first problem, it's really one big question. So, extrema, back to the blue here. Points of your extrema. Well, there's a max or a min. Which one? There's a min. And the green lines tell you this, right? There's a minimum. It's a relative min. Because that's a test. Absolute mins are where you test on a defined closed interval. Relative min at -1, comma. I don't actually know what the min value is. How would I find it?
Put it into the original.
Original. Because if you put it into the derivative, you're going to get 0, right? So, -1, we can do this in our heads. -1 minus 2 is -3. Cubed is -8. Now stop me, because -2 times -2 times -2. -8. Times -1 plus 2, so it's 1, right? No, just a second, negative. Did I do -1? It's -3, I said. I was going with -2, wasn't I? Yeah. -1. See? Stop me when I don't do arithmetic, and you guys, your puzzle looks maybe. Good. -3 cubed. And I realized when I plugged in -1 with the +2, what I had done wrong. -27. That's low, it's low as it goes. The actual minimum value, if I ask you that, is negative 27. The point though, because we're gonna be sketching a graph, I'm gonna want a point. It's a minimum there. Why do we know it's a minimum? Well, we have the stick graph to remind us. It's a minimum at that since f prime of x, what do we say is the little recipe to explain it?
Switches signs.
Switches signs from, yeah. From negative to positive, right? It's going down and going up. Now, I don't care if you use the word but if you're going to do it this way, circle it just so I don't think your dash, sometimes people's pluses look like T's or N's and stuff like that too, right? If you want to write the word negative and positive, that's great too. Then, so this is something we're going to throw on our graph later on. The other thing is it's increasing and decreasing. So, we'll start with decreasing. Decreasing on the interval negative infinity, open interval, to negative 1. Since the derivative is less than 0, and increasing on, now, question, is it increasing on this whole interval, or do we have to take a break at 2 and say it's increasing up to 2 and then after that? Don't take a break.
Okay.
Kit Kat, nope. We can have a finite, which means a countable number of values where it's 0. If you had a zone like from 2 till 3 at 0, like it was a piecewise function, then we couldn't say it. But since it's just at the point, it's increasing on negative 1 to positive infinity. Since f prime of x is greater than 0, and I would never ding you if you missed this. It's supposed to be a greater than sign. Greater than 0. F prime of 2 is equal to 0. Within that range. It's only equal to 0 at once, a countable number of times, right? Okay. So as long as it's a countable, a finite number of times. So we got our increasing and decreasing, and we got the stick diagram to show us. Basically that stick, this line right here tells us everything. We just got to know how to interpret it, right? Now, the other things we need is concavity. Concave up, concave down, and we call it an inflection point if it switches from curvy up, curvy down. How do we find concavity? Second derivative. Okay, time to change colors. That means with my second derivative, I can find inflection point and concave. Points, possibly, we don't know. And concave. So, F double prime. Of course, if this was a simpler function, I'm going back to here, I would suggest you multiply it up. But this isn't simpler. I'm thinking we should go with what we have right there, okay? So that's single derivative. 4, I'm going to just remember this. 4x minus 2 squared x plus 1. I can't remember things very well. So, first, I'm going to write down from the previous step. F prime of x. Don't let me write it down. 4. Is it x minus 2?
Yes.
Squared. X plus 1?
Yeah.
Okay. So now my second derivative. Okay. I'll do the derivative of the first thing, so 8. X minus 2. The exponent becomes 1. Do the derivative of the inside, it is 1. Second thing left alone. So write it down. Plus. First thing left alone. Derivative of x plus 1 is 1. This one isn't as nasty. That, with polynomials, when you do the derivative, it tends to get that way. Now, because we're looking for possible zeros, right? Possible inflection points, I'm going to set it equal to 0 right now. Where does the second derivative equal 0? And we'll do the factor. Now, 8 and 4 have a common factor of 4. X minus 2, and you yank those two things out of both. Now, 8 divided by 4 is 2. X minus 2 is gone, so x plus 1. I've taken out one group of x minus 2, so I've got one left over. Group the like terms in the square brackets, and we're set. So 2x plus x is 3x. Plus 2 minus plus 1. You guys are triple dog checking my arithmetic. And I've got it wrong, don't I? I see it right now. Did you guys? I was thinking something silly. 2 minus 2. That's it. So now I've got 12x. 3 times. This time I caught my own mistake. The zeros are easy to find. Possible inflection x values. So, I'm going to do a quick number line. I'll do it to the right here. With 0 and 2 on. I'm going to put 12x, my second derivative here. I'm going to put x minus 2 here. Oh wait, are we caught up? Do it. Let's analyze this. 12x, add 0 at 0, negative values are negative, positive values are positive. X minus 2 is a 0 at 2. Higher is negative, lower, or higher is positive. My hands are writing faster than my mouth can speak. Okay. Plus, minus, plus. What does this mean? This means, and I'm just doing a rough sketch like I did with the stick sketch. This means curve up, switches, curve down, switches, curve up. Now, it might not necessarily look like that. This can be misleading, right? And in this case, it's not going to look like a sine or a cosine function. But just keep this curve up zone and stuff in mind, because this at least tells us we've got concavity zones. So let's just go with this inflection points. Inflection points, as the second derivative switches signs, we've got a point at 0, comma, in the original function. Take a look. Negative 2. That's the 8 plus 16. Negative 16. Using the original function. The other inflection point is 2, comma. When you put 2 in there, it's a 0. Because it'd be 0 cubed. Okay, and concave up, concave down. cavity. Up on two different intervals. Negative infinity 0 and or union with 2. Calculate down. My spelling is crappy. 0 to 2. We've got those because of the sign of the second derivative. Lastly, is there any asymptotes on this? No, because you don't have a rational function, there's no asymptotes on this. Our intercepts. We pretty much have our intercepts. Always look for intercepts here, where the easiest one is plug it in 0. We've got that intercept. This is one of the intercepts. You could probably also see, at a quick glance at the original function, that negative 2 would give you a 0 as well, right? Because you're going to make sure you plot your intercepts. I'll just jot that down here too. So our intercepts, even though they're already listed, I can list them. X and Y intercepts. The easy one, when x equals 0, you get negative 16 out of it. We already had 2, 0 in there. A quick look at your original function, since it's factored, tells you that negative 2, 0 is another value of where you get y equals. Now to throw this whole thing together as a graph, I'm going to just put it on another page here just because. Now we do a careful sketch. That means you're careful where your x values are, but it does not have to be drawn to scale, if you follow. So, it does not have to be drawn to scale. So you're going to go through the whole thing. Like I said, start with your x-intercepts and your y-intercepts. So, I'm going to tick, tick. So there's my negative 2. I've got an intercept. Now, obviously, if this is a spacing of negative 2, I'd never fit, what, negative 27 is my min, right? So I'm going to just call this about here. I'm sorry? Oh, it's a 0. It's one of my intercepts, right? Just 0 and 16 is, negative 16 is what I was just going to plot. But 2, 0 and negative 2, 0. Now, I did the negative 2 because just looking at this, you could probably see negative 2 would give me a 0. I didn't work it out. That's for that. Now, I'm going to approximate this. I might shift it up or down. It's x negative 16. It's more. Isn't it 16? Yeah. The other x-axis thing, so 1, 2. And that'll be my 2, 0. Now, I had another point, so I want to put all the points that I've come up with. And we happen to have our inflection point already plotted, 0, negative 16. Our minimum was it negative 1 with 27? Negative 27?
Negative 1.
So if this is negative 16, you're just making sure it's significantly lower. And there's our min. Negative 1, negative 27. Now it's join the dot time. I'm thinking, though, remember my green stick diagram from the first derivative, increase, decrease. It decreases on...
Till negative.
Yeah, let's just zip back here, though. This is the way you're going to decide here. Till negative 1, it goes down. Then it goes up, takes a rest, goes up. So I'm thinking stick diagram before I draw this. Down, up, 0, up. A 0 meaning like it's, how is that gonna look? Do you guys imagine this? It's gonna look like increasing, smooth. And do you guys remember from grade 11? When you have a factor that's odd, and it's greater than 1, odd degree. Do you guys remember that? That means that it kind of goes, it doesn't go straight through the line, it goes, oh, I drew it too curvy there, but this is what happens. Do you guys remember those zeros? Multiplicity of the zeros is what you guys called it then? That's what this is. Right? So you can actually tell that from the start
Can you
here.
scroll down just on the page?
Which, the diagram or the,
Right here,
okay, which first or second?
second, I just want to know.
Sure. And while we're here, that's the next thing. Now we got to figure this out. Concave up, concave down, concave up. Right? Now, it's not going to look like a sine or cosine function the way that looks. That's just to remember things. So how can we be going down and then up, and it's supposed to be concave up, then down, but it's still increasing, and it's concave up then, right? Hey, doesn't it kind of look like that then? Ah, so this is what's going through my mind with those stick diagrams, right? So I'm thinking, I'm going to try to draw my best here, deliberately make a change in concavity at 0.16, change in concavity and at 2 and 0. It should look like what's just disappearing, right? Hardest part for me on here is to do my freehand sketch with markers because it's easier on paper for me. But you guys go for it, I go for it. Not too shabby. Of course it goes beyond, and show that it goes beyond the x-axis, like it goes above it, increasing forever. There's your sketch.